Good evening, everybody. I am Siddhant, and today we are going to have a discussion about this new paper which presents a new message passing paradigm called Cooperative Graph Neural Networks. So, we all know that graph neural networks are really popular architecture these days, and the whole field of graph machine learning it has some foundational ideas of iterative computation of node representations of an input graph, right? So at every layer L and for every layer L plus 1, so if we start at node U at layer L, this node and every node will propagate the messages from their node to their neighborhood, right? And for the layer L plus 1, the receptive field of this node will get bigger and bigger, right? But in this paper, they present a new framework of message passing in which every node can be viewed as a player of a multiplayer game, and that node can choose either to listen and broadcast, or to isolate. So these choice of actions, we can say we will have a deep look in the paper how these things are getting formulated. But this approach offers a more flexible, dynamic, and directed form of message passing paradigm, which can be also uh, termed in the form of control based message passing paradigm, where each node can represent or determine its own strategy based on their initial state and effectively exploring the graph topology while learning, right? So for a long time now, all the standard message passing paradigm and the graph neural networks which have been proposed throughout the years, they follow a very rigid scheme of iterative based node computation and updation of their representation layer by layer, right? But in this paper, the fundamental idea is each node's representation based on the aggregate of message flowing from the node neighborhood can should be controlled, and each node should determine whether it wants to listen or broadcast or isolate from the message flow from its neighborhood, or message coming from the L layers of neighborhood. So we all know that there has been well-known limitations to standard message passing schemes such as oversquashing. So what oversquashing is, in order to receive an information from k-hop neighborhoods, a message passing neural network needs to flow the message for at least k layers, right? So if you want, so let's see here, if you want node U's representation to be reached to node V's representation, which is on a second hop neighborhood of node U, so you will need two iteration of graph neural network, right? But what it does is, it typically implies an exponential growth of node's receptive field, and this growing amount of information needs to be compressed into a fixed size node embedding, and it possibly leads to information loss. This phenomena is referred as oversquashing, and oversquashing is mainly observed where the edge has highly negative curvature, right? Because let's suppose if you would like to flow your information from node U to node W, and there is node V, right? So if you want to have a long range interaction, if you want to capture a long range interaction to pass the representation of node V to U to another node B to W, you will need at least 4 layers of GCN, right? But here, when the messages are coming from all of the neighborhoods of U, then this fixed size vector cannot compress a lot of information which can be utilized, and this information turns out to be really oversmoothed, or here we say oversquashed. So this is the main motivation behind this paper, that whether a node would like to listen or interact with the message flow or not, right? So allowing each node to decide how to propagate information flow from or to its neighbor. This enables a more flexible flow of information, right? So you can see in the example figure 1, if a node W, this node, would like to listen information only from its neighbors, you can say neighbors of node U, then it can only listen the information in this subgraph, which is colored by gray. The information flow becomes more complex if nodes have different choices across layers, since we cannot anymore view the process merely focusing on a subgraph. This kind of message passing is then dynamic across layer. This means on each layer L to layer L plus 1, the computation graph will not be same. Okay, so the main idea is we need to learn whether a node would like to listen to a particular neighborhood, or it would like to only broadcast its message to a particular neighborhood, right? So in this paper, they regard each node as a player that can take following action: standard, listen, broadcast, or isolate. So standard action will follow the standard message passing. Listen will follow only listening of the information coming from the neighborhood. Broadcast will follow broadcast to the neighborhood that listen. And isolate is neither listen nor broadcast, effectively isolating the node from the neighborhood. And it can be also seen as removing all edges. So these interplay between actions and ability to change them locally and dynamically makes the overall approach richer and allows to decouple the input graph from the computational one. That incorporates directionality into message passing and provides us more control over which nodes needs to their information to be fused with another or aggregated with their neighborhood. So for example, if a node can only listen to these neighborhoods that are currently broadcasting and vice versa, right? By choosing the actions listen, and standard, or standard, isolate standard, or etc. The main contributions are as follows. So we will see how COGNNs work and what is the paradigm they follow to gain such control over message passing. But here we can also see a really important comment about Weisser-Lemon algorithm, that authors claim and prove that their approach is more expressive than one WL test, right? Which is and more better suited for long range tasks due to this adaptive nature of their approach. And we will discuss the empirical results, what this approach achieves. So let's have a rough look over the COGNN approach. Here you can see a formalism of standard message passing, right? As we all know that in the standard message passing for every layer L, and if you would like to update the nodes representation for layer L plus 1, then you take the initial representation of that node, you aggregate the feature representations of all nodes which are in the neighborhood of our current node, and we aggregate them using some sort of permutation invariant function. You can say a permutation group phi, which is, so phi is a permutation invariant function such as sum or mean or max, right? And then we update using a permutation equivariant function. So this is the standard message passing paradigm. What COGNN does, first of all, as we already discussed, they treat each node as a player of multiplayer game. The state of the current node will be directly the feature vector of our nodes in the graph, right? They employ two type of networks. First is environment network and another is action network. And this COGNN follows a two-stage paradigm. Okay, so first of all, they will use the action network to sample the actions, and then they will use environment network to update or to perform the message aggregation. So in stage 1, you have an action set for each player of their own current state. You take that current state and the neighboring node's current states, and you learn an action set which is here in the paper, which is described as a probability vector over 4 actions. And you take an action, so every player will choose an action. The action can be isolate, standard, listen, and broadcast. On the basis of that particular action, the environment network will update on the basis of current state of the acting node and a subset of neighborhood. So here you can see we take full neighborhood for a layer L, right? But here they only take a subset of neighborhood. So what subset will contain, it will be determined on the basis of the action, and only those nodes will be used. If the action is isolate, then subset will be a null set, and it will only use the current state to update or to reassign the current state, right? But before diving into this, we can let's have a look on a really important tool which is employed in the paper, and it will help us to understand why the author chose to use this tool. We will see that later. So straight through Gumbel softmax estimator. So in our problem, what we want to do is we want to learn a categorical distribution over the action set, right? But the set of, so this categorical distribution will be predicted using the action network, and the thing is the categorical actions are not differentiable, and this thing poses a huge challenge in gradient based optimization, right? We cannot back prop through any distribution which is not differentiable. So Gumbel softmax estimator, what it does is it provides us a way or a reparameterization trick which gives us an approximation of that categorical distribution which is continuous and differentiable, right? So in our problem, we are interested in learning a categorical distribution over action set omega, let's say, and which can be represented in terms of a probability vector P, and the elements of P will store the probabilities of different actions, right? So we have only 4 actions in our action set in this paper. So probability vector will contain 4 values for each action, right? But this is not a differentiable set. So what Gumbel softmax do is it will give us an estimate of P. So we will call it the Gumbel distributed vector G, and G will be an estimate of the categorical distribution P, and that will be continuous and differentiable as well. But authors only use this Gumbel softmax reparameterization trick while backpropagation, not on forward pass. And let's have a look why they do not use the Gumbel softmax estimator in the forward pass, only backward part. Coming over to formal description of COGNNs. So as I already told you, COGNNs contain 2 networks. First is action network and another is environment network eta. So let's suppose we have a node V as an agent, and it on the layer L it contains the states as feature vector HV, right? So our action network pi will take the feature representations of node V as input along with all of the neighbors of node V, which are HU at layer L, as input, and it predicts a probability vector P over 4 action set, right? So another important thing is both of these networks are GNNs only. So our action network is also a GNN and environment network is also a GNN. So action network, what action network will do, it will take the whole neighborhood of node V, right? And the current state of node V, and it will give us a probability vector P, which is categorical distribution. So we cannot, so right now we will not convert it into the learned probability vector G, but action for so the action for V is sampled from probability vector P only, right? So when the action is sampled, according to that sampled action, the environment network will act, and environment network will be utilized to update the representation of node V. So here is the formal, you can say, message passing paradigm of environment network, where if the action is isolate or broadcast, then then our updation set will not contain anything, and the feature vector of HV will be reassigned to the layer L+1. However, when our action contains standard or broadcast action, then all of the nodes U of neighborhood of V, all of them are aggregated to update the message, to update the feature vector of node V at layer L+1, right? So previous state and neighbors are chosen if the action is broadcast or standard, right? So here is how they are trying to control the message flow. All right. So please let me know if you guys have any questions or anything regarding this.
So, Siddhant, I would like to ask one question.
Right, yeah, sure.
So, as they have proposed that the message passing will be dependent on which action, or you can say which type of flow mechanism a node can decide on its own. So, how can we say that specific action out of the four, when selected by a node, is the most optimal one to, run uh, for a run in graph neural networks?
Right. So this is the scenario where the Gumbel softmax or the straight through Gumbel softmax trick will come into the play. Okay, so if we have a set P and it will contain probability for each action, right? So what they are doing, they are not using the typical RL sort of paradigm to control the message passing, right? They do not have an explicit reward formulation, whether the action sampled or the probability for action is the optimal or not, right? Using some sort of explicit reward, but the reward term is a really implicit thing here. So what they are doing is they are making the message passing more adaptive to the task, right? So this COGNN architecture is not task agnostic. It can update its flow of message or the construction of computational graph on the basis of the task. So the loss here or the reward will be tuned, or as per your question, the action set will be tuned on the basis of loss, which can be such as node classification tasks, so NC loss. So at the time of backpropagation, uh, both of these networks are trained together, right? Why? Because they are using straight through Gumbel softmax at the time of backprop. So the weights, so the loss which is coming from the tasks such as node classification task, it will also be propagated back to the action network, right? So if those set of actions is not optimal, so in the next epoch of the training iteration, the action set will be tuned, because now our action set is not a categorical distribution, it is an estimate, it is a continuous and differentiable estimate g, for that particular probability vector. So this is how the action set is the most optimal action set for the task. So this is the this is a really cool trick which is adopted here to mimic the RL, but not explicitly using the RL, because explicitly using the RL is also, as we all know, it is also really difficult to get stability, and they also would like to make the architecture less computational costly, right?
Got it.
Sure, thanks. So this is the formal paradigm of COGNNs. Let's have a look on conceptual properties this paradigm offers, right? First of all, as I already told you, it is task specific, not task agnostic. And we all know that the standard message passing models are completely task agnostic. They cannot be changed if on the basis of tasks, such as standard MPNNs does not know whether the embeddings getting computed or message getting flowed is as effective for node classification task, or it will be used for downstream graph classification task, right? And these COGNNs determine a computational graph which is best suited for target task. We can also see COGNN update as a directed form of rewiring, right? Because in this, on the basis of choice of action, an edge can be dropped, or an edge can remain undirected, or an edge can become directed, or the whole message passing can be of a standard form, right? So let's have a look at how it is directed, or can be termed as directed rewiring. Because if there are two nodes and one node choose to listen without broadcast, then the edge is dropped in between these two nodes, right? If both neighbor apply standard action, then there will be an edge and it will be an undirected edge. If one node chooses to listen, other node chooses to broadcast, then the edge will become directed, right? And these different, so now we can assume that the proposed MPNN can be seen as operating on a potentially different directed graph, which is induced by the action choice at every layer. So at the time of updation, the set where we are aggregating the feature representation is not the whole neighborhood. Instead, it will be the corresponding nodes from the existing edge at layer L, right? Apart from that, COGNNs do not operate on a prefixed computational graph. Rather, they learn a computational graph which is dynamic across the layers, and it is feature and structure based as well. So standard message passing is completely determined by the structure of graph. Two nodes with the same neighborhood get same aggregated messages. But here, action network can learn different actions for two nodes with different node features. So by choosing different actions, red node and blue node, that enables different messages for different nodes, even if node neighborhoods are identical. So COGNN is also asynchronous and efficient. So they have done a lot of experimental analysis to ensure that COGNNs are also parameter efficient for same policy network, and as a result they are comparable to the number of parameter of their baseline models. On the term of expressivity, here you can see a proposition which proves, and there are proofs in the appendix, so we can discuss them on our Slack channel. COGNNs are parameter. So yeah, the thing is, as you guys can see that COGNNs are parameterized by two networks. So it uses two graph neural networks, but still a GNN, the expressivity of GNN is bounded by one WL test, right? So how can you say that expressive power of COGNN is not bounded by one WL, even if it is having the same GNNs only, right? So COGNN learn at every layer for each node a probability distribution over action, right? These learned distributions are identical for two isomorphic nodes. However, the process relies in sampling actions from these distributions. So we can see that clearly the sample from identical distributions can also differ, right? So COGNN models invariants in expectation and the variance introduced by sampling process that helps to discriminate the nodes that are 1WL distinguishable. So yeah, this is how, and uh, with the proof author claim that the COGNN architecture is more expressive than 1WL test and the standard MPNS. So long range tasks necessitate to propagate information between distant nodes, as we saw in our first example, to propagate a message from layer 1 to layer fourth or fourth hop neighborhood, you need to deploy 4 layers of GNN. And dynamic message passing paradigm is so this sort of dynamic message passing paradigm is highly effective for such tasks, right? So coming over to over squashing again. So in their earlier work, they formalized the over squashing as the insensitivity of R layer MPNN output node to the input features of a distant node V, and it is expressed through a very famous Jacobian bound, which is which is bounded by the adjacency of power R. So R hop receptive field is bounded through the adjacency of power R, right? This is exactly the bound. You can see here as well. So there are a lot of graph rewriting techniques which are proposed from different set of authors and a lot of people from the community that modify the adjacency matrix so as to increase this upper bound and here hence reducing the effect of over squashing, right? And theorem 5.2, you can have a look at the proof as well. They claim that it results in maximization of the bound on the Jacobian. And for the oversmoothing, so oversmoothing refers to the tendency of node embeddings to become increasingly similar over the graph with the increase of number of message passing layers, right? So if the same message is getting passed through L layers with R hop neighborhood and employing by R number of GNN layers, the message will get smoothed out and will become increasingly similar. So oversquashing can also be mitigated through gradient gating based mechanisms, which adaptively disables the update from node from the neighborhood with similar features. So this COGNN paradigm also uh, mimics this gradient gating mechanism using the choice of action, broadcast or isolate actions. Coming over to experiments, they proposed a new sort of task, which is also a key point here to see whether they are achieving uh, the control which is actually required to solve difficult tasks, right? So they formulate a new data set called root neighbors. So what is root neighbor? The task is a regression task. So given a root node of a tree, so the node R, which is a root node, and the task is to predict the average of the features of root node neighbors of degree 6. So we want to predict the average of features of all the neighbors which have degree is equals to 6, right? So here you can see there are two neighbors which have degree is equals to 6, and the prediction label will be xu plus xv divided by 2, right? So this will be the target value. So you can already see the complexity of this task. First, MPNN or message passing neural network have to identify the neighborhood, the neighbor nodes which have degree 6, right? And then it will have to compute the target as the HU plus HV divided by 2. So this will be our target prediction value. So they tried different sort of MPNNs such as mean GNN and GCN GAT. Apart from that, let's have a look again if I have missed a point here. Where? So they have characterized the GNN architectures in such a manner that it can be some GNN, mean GNN, normal GCN or GIN, right? So it is based on the aggregation function choices, right? And they have performed exhaustive experiments with changing the sum GNN and mean GNN or the choice of aggregator function for action and environment networks both. Coming over to this new task, so you can see the reported results and where so GCN and GET are only marginally better than random baseline, and so mean GNN and other graph sage and gate, so all of these performed really poorly in this task, but mean GNN performs substantially better than the random baseline, right? But you can see the performance of COGNN. It performs really good, and they so what they did is, and they claim that the best result is achieved by COGNN having sum for action network and mean for environment network. Okay, so this new task and new dataset can also be used for further research and to try and do exhaustive experiments whether uh, transformer based MPNNs or other MPNNs can perform in these sort of difficult tasks as well, right? And they test their proposed approach over standard node classification and graph classification task. So right, and you can see the results in the both task, adaptive message passing or the control based COGNNs performs really good, right? So this was the crux of the paper. I really liked the paper, and I would really love to have experiments run by my own and to see whether we can take this paper and learn from it and do more experiments on other sort of data sets and explore this new form of message passing. This is all from my side. If you guys have any questions, then please ask.
I guess there are no more questions.
Sure. So we can wrap up our this uh, paper reading session on this, and if you guys have any questions, then you can please follow up on Slack, and I will surely try to discuss more on this paper.
Sure,
Thanks.
Siddhant.
Thanks. Have a nice day.